Hello everyone, starting with biomolecules. It is a chapter of your organic chemistry. Let's get going. Biochemistry. Okay, so biomolecule falls under the portion of your biochemistry, which is the study of what goes inside the living system. So, if you want to know what is the chemistry of the living system, then you should go with your biochemistry. Coming up, biochemistry mainly has two portions, which is the bioorganic and the bioinorganic. Under the bioorganic portion, we have the chapter of your biomolecule, which consists of carbohydrates, proteins, nucleic acid, and the others category, right? Under the others category, we have your lipids, vitamins, and hormones, right? Moving on to carbohydrates. So, in the ancient days, it was believed that carbohydrates are nothing but they are just the hydrates of carbon, okay, and have a general formula or satisfy the general formula of CxH2O whole y, where x and y are a few integers, okay. So, integers means they are perfect numbers, they cannot be any decimal value, right? So in the ancient days, it was believed that carbohydrates are nothing but they are hydrates of carbon, which has a general formula of this. For example, if we take the example of carbohydrate, there is glucose and fructose. They have the formula of C6H12O6. So you can write this formula as C6H2O whole 6 in this way, right? So since this is satisfying this formula, so it was believed that it is a carbohydrate. But though we want to represent the carbohydrates as hydrates of carbon, which means this formula, but there are also few compounds which satisfy this formula, means this above formula, but are not carbohydrates. For example, if we take the example of your acetic acid, which is CH3COOH, we can write acetic acid in this form, which is C2H4O, and finally in the hydrate form, which is C2H2O whole 2. Okay, so this formula is satisfying the formula of carbohydrates as we have seen above, right? But this is not a carbohydrate, right? Acetic acid is an acid. This is not a carbohydrate. And also there are few compounds which do not satisfy the formula of the CxH2O whole y, but are the carbohydrates. For example, we have your rhamnose, right? This is an important question. The exception to the CxH2O whole y rule, which is rhamnose, which have the formula of your C6H2O H12O5. I'm sorry, this do not satisfy the formula, but it is carbohydrate. So that means that there is some flaw in the definition of carbohydrates, right? So people came to a modern definition of carbohydrates, which says that carbohydrates are optically active polyhydroxyaldehydes or ketone, or any such compounds, means the derivative of aldehyde or ketone, which gives this on hydrolysis. So carbohydrates are nothing but they are the optically active polyhydroxyaldehyde or ketone, or any compounds which gives these products on hydrolysis, which produce this aldehydes or ketone on hydrolysis. Coming to example of a carbohydrates, there is your glucose, which is D-glucose, and L-glucose. This is the structure of D-glucose, which is CHO. Here is your HCHO. This is your HCHO. Okay. Now, if you this is your D-glucose. Now, the best thing, if you want to remember the structure of L-glucose, you have to memorize or you have to learn any one. If this is D-glucose, then we take a mirrors. I assume this to be a mirror. Okay. Zooming out just a second. Okay. So I consider this as a mirror. I just reflect it. I just do nothing. I just reflect it in the mirror, right? Okay. After the reflection, we see that L-glucose is obtained, right? See here the changes are occurring. Just see the functional group present. You can clearly understand the structure of D-glucose and L-glucose. Moving on. Here is a few points about D-glucose. It is a carbohydrate, plays an important role in biochemistry, most abundant substance in biomolecule, the omnipresent fuel in biology, right? Fuel means if you burn this glucose, you obtain energy, right? So for the better understanding for this, I gave you the example of petrol. When you burn petrol, you get energy in the form of heat. Similarly, if you burn glucose, you also get energy, right? So here there I am discussing about your nomenclature of your biomolecule, which is the glucose, right? So D-glucose, D means D is just a configuration. D does not mean your dextrorotatory or levorotatory. D is just the configuration. Plus means it is dextrorotatory and glucose means sugar, right? This O portion mainly means sugar, right? Now coming up is the source, okay? From where can we get glucose? Now we know plants perform photosynthesis, and plants perform photosynthesis with the help of sunlight and carbon dioxide and hydrogen, right? And external conditions are chlorophyll and sunlight to give your glucose, right? What is chlorophyll? Chlorophyll is a metal ion complex of your magnesium. Moving on. Now this graph says that this chart is important, which says that D-glucose is interconvertible to your starch. You can convert glucose to your starch, also to glucose and also to glycogen. Okay. Now here you can see that D-glucose is converted into your glycogen, cellulose and starch. Right. So what is starch? Starch is in a plant seed as a starch is stored in the plant as a seed and the fruit. Okay, the cellulose from the framework structure of the plant, right? The cell wall of the plant is made up of your cellulose, right? And glycogen is present in the animal starch. Glycogen can transferred by blood. It can also be stored in the liver, right? Glycogen, the main function of the liver is to convert glycogen to glucose, right? Okay, so when the glucose concentration, and we know that when the glucose concentration increases, we have diabetes. Okay. Moving on, uses of biopolymer of glucose. So glycogen is used for long-term energy storage. It is used in liver and muscle, as I have mentioned just now. Moving on, the starch is stored in the food, which is your potato, right? Potato contains starch. And cellulose, it is used for making the money. Means the currency which we use today is made up of cellulose. Means the Indian currency version, which is the sort of a paper, right? So that thing is made up of your cellulose. In the wood, we can also use that cellulose, and in the cotton industry for manufacture of our clothing, we can also use cellulose. Moving on, now we will classify carbohydrates on the basis of various factors. Let's change the color of the ink. All right. So classification of carbohydrates. So on the basis of functional group, carbohydrates are classified into two parts. One is the polyhydroxyaldehyde and another one is polyhydroxyketone. If the aldehyde group is present, then it is called polyhydroxyaldehyde, and another one is called the polyhydroxyketone, right? The example of this is polyhydroxyaldehyde is your glucose, and the example of your polyhydroxyketone is your fructose, right? Now on the basis of reducing nature, now whether the carbohydrate is reducing or non-reducing, on the basis of that you can classify carbohydrates in the two types. One is your reducing sugar and another one is your non-reducing sugar. Okay, under the category of non-reducing sugar, we have the example of your sucrose. Now you have to remember this, sucrose is non-reducing, and your reducing sugar, under that we have monosaccharides, fructose, glucose, maltose, lactose and many other categories, right? Moving on. Now on the basis of sweetness, we can classify carbohydrates, right? So on the basis of sweetness, carbohydrates can be classified into sugar and non-sugar. Whether it is sweet, then it is sugar, and if it is non-sweet, then it is called non-sugar. A thing to be noted here is that saccharide comes from the Latin word which means saccharum, which means sugar. Okay, so let's make it clean. It's looking dirty, right? So moving to the next portion. Now on the basis of number of carbon atom, we can classify the carbohydrates. If there is 3 carbon atom, then it is triose. If there is 4, it is called tetrose. If there is 5, it is pentose, and if 6, there is hexose. Now if CH group is present, then we call it as aldose, and if C double bond O group is present, then we call it as ketose. Now this is a very important portion, so let's change the color of the ink. Okay, just read this. This is important, I mark here. So if a carbohydrate has 4 carbon, okay, let's highlight. I'm saying here that, so if a carbohydrate has 4 carbon and CHO, then it is called Aldo Pentose. Why Aldo Pentose? Why not Aldo tetrose, because it is said here that if a carbohydrate has 4 carbons, so there is your tetrose group, right? And another CHO means the aldehydic carbon is also counted, so it is called Aldo Pentose. Similarly, if a carbohydrate has 5 carbon and one C double bond or the keto group, then it is called ketohexose. Right, now on the basis of the product of hydrolysis, you can classify the carbohydrates into monosaccharides, oligosaccharides, and your polysaccharides. So after hydrolysis, okay, so monosaccharide do not undergo hydrolysis. Okay, so here it is an important factor. So monosaccharide do not undergo your hydrolysis. So after hydrolysis, if there is 2 units, 2 to 10 units we get, then it is called oligosaccharides. And if we get more than 10 units, then we call it as more than 10 units, then we call it as your polysaccharides. For example, starch, glucose, and glycogen. And under this we have sucrose, maltose, and here this glucose, ribose, and your fructose. This is monosaccharides. Now before moving on to the preparation of glucose, I would like to revise up to how much I have said. Okay, so let's get to the first portion. All right, so we have started with the chapter of biomolecules. So biomolecule is a part of your biochemistry, which is the study of what goes inside the living system. Under the biochemistry, we have 2 portions. One is the bioorganic, another one is the bioinorganic. Under the bioorganic portion, we have the chapter of your biomolecules. Biomolecules have 4 parts: the carbohydrates, the proteins, the nucleic acid, and the others category. Under the others category, we have your lipids, vitamins, and your hormones. Right, so moving on, under the carbohydrate category, so what is the carbohydrate? So in the ancient days, it was believed that they are nothing but they are the hydrates of carbon, which have the general formula of CxH2O whole Y, where X and Y are the integers. Now the example of carbohydrate is your glucose and fructose. Now glucose has the formula of C6H12O6. We can represent it as the hydrate of carbon as C6H2O whole 6. We don't want to represent the carbohydrates as the hydrates of carbon, but this is not always true, because if we consider the example of acetic acid, which is CH3COOH, it can be written as C2H4 whole C2H4O2, and can be written in the hydrate form, which is C2H2O whole 2. But this is not a carbohydrate. Acetic acid is not a carbohydrate, but it is satisfying the formula of CxH2O whole Y. And there is other example of this, other exception to this rule, that there is a lot of compound which do not satisfy the above formula but are carbohydrates. I told you to remember the example of your rhamnose, right, which is the C6H12O5. This is the carbohydrate, but it do not satisfy the above formula. Next, I have told you that so there was a flaw in the previous definition, right? So what did people do? People came to the modern definition. They said that carbohydrates are nothing. They are optically active polyhydroxyaldehyde or ketone, or any other compounds which can produce this on hydrolysis, right? Carbohydrates are optically active polyhydroxyaldehydes or ketone, or any other compounds which can produce this aldehydes or ketone on hydrolysis. The example of the carbohydrate is can be given as your D-glucose and your L-glucose. So I have discussed the structure of your D-glucose and L-glucose. Moving on, I told you a few points about D-glucose. I have mentioned that D-glucose is a carbohydrate. It plays a prominent role in the biochemistry. It is the most abundant source of energy in the source of fuel in the biology, the most abundant substance in biomolecule. So D-glucose, here I have discussed the nomenclature. Plus means dextrorotatory, which will rotate the plane of polarized, right, PPL, plane polarized light. That is the unidirection light. It can bend down, it can bend up. So on the basis of that, there is 2 subdivisions. One is dextrorotatory and another is your levorotatory. D-glucose is dextrorotatory, so it is represented by plus sign. Now this D stands for your configuration. This D has nothing to do with your this D has nothing to do with your optical activity. So let's write here, this thing is based on, it became big, just a second. So let's write here on the basis of config, right? And so let's pull an arrow here. All right. Okay, so this D represents just the configuration and nothing to do with the optical activity. Moving on, this O's portion means sugar. Okay, now I have discussed about the source of your carbohydrates, which I have already said that carbohydrates come from the photosynthesis in plants from the CO2 and H2O, and the external conditions are the sunlight and your chlorophyll. Now, what is chlorophyll? Chlorophyll is a metal ion complex of magnesium. You have to remember this. Question may come. Okay. So D-glucose is interconvertible to your starch, glucose and glycogen, and also the cellulose. This will be your cellulose, not glucose. This will be cellulose. Okay, I hope it's understood. Moving on. So here D-glucose I have shown how it is convertible to starch. And what is starch? Starch is found in the plant seed as food. Cellulose from the framework of the structure of plant, which is the cell wall. You can write here cell wall. Okay. Moving on, coming to glycogen. So what is glycogen? Glycogen is found in the animal starch, right? It can be transported by a bloodstream. Okay. Now coming to the uses of glucose. Glucose, of course, the biopolymers of glucose rather. So glycogen can be used as a long-term energy storage mechanism in liver and in muscle. Starch is found in the food as in potato. Now the paper, I have already mentioned that paper can be used for the economic purposes, like the making the paper of the money, and also in the woods and also in the cotton industry for the textile. So moving on to the classification of carbohydrates. Now on the basis of functional groups, carbohydrates can be classified according to two categories. If the aldehyde group is present, then it is called polyhydroxyaldehyde. If the carbohydrate group is present, then it is called the polyhydroxy ketone. Okay, if the aldehyde group, it is called polyhydroxyaldehyde. If the ketone group, it is polyhydroxyketone. For example of that polyhydroxyaldehyde is glucose, and example of polyhydroxyketone is your fructose. Now, on the basis of your reducing nature, carbohydrates can be classified into two parts. One is your reducing sugar, and another one is your non-reducing sugar. Under the non-reducing sugar, we have your sucrose, and under the reducing sugar, we have monosaccharides, which is your fructose, glucose, maltose, lactose, which are not monosaccharides, they are disaccharides, but they are reducing. Now, how to find out which one is sugar is reducing, which sugar is non-reducing, I will tell you in the later sections of this chapter. Okay. Moving on the basis of sweetness, I can classify carbohydrates into two categories. One is the sugar, one is the non-sugar. Okay, so you have to keep that thing in mind. I'm sorry, just a glitch. So, all right. So on the basis of sweetness, you can classify carbohydrates into two parts. One is sugar and one is non-sugar. So saccharide comes from the Latin words means saccharum, which means sugar. Now on the basis of number of carbon atom, there is triose, tetrose. If 3, 4, 5, 6, so it is called triose, tetrose, pentose respectively. If 6 are present, then it is called hexose. If CH group is present, then it is called aldose. If C double bond O group is present, then it is called ketose. Now this is a very important portion. Okay. So if a carbohydrate has 4 carbon and 1 CHO group, then it is called Aldo Pentose. If a carbohydrate has 5 carbon and 1 C double bond O group, it is called ketohexose. Now on the basis of number of products on hydrolysis, it can be classified into three parts. One is the monosaccharides, one is the oligosaccharides, one is the polysaccharides. Now monosaccharides do not undergo hydrolysis, right? Oligosaccharides undergo hydrolysis to give 2 to 10 units, and polysaccharides give more than your 10 units. Now example of monosaccharides are glucose, fructose, ribose. Okay, these are the important parts. Just a second. So this is the example of your monosaccharide. These are the example of your disaccharides, and here lastly your starch, glucose and glycogen from the example of your polysaccharides. Now moving on to a very new portion, which is your preparation of glucose. Okay. Now we can prepare glucose primarily by the hydration of your cane sugar. Now what is hydration? We can perform hydration by boiling the glucose in the boiling the sucrose. This is your sucrose. Okay. Now we can perform we can boil the sucrose in enzyme invertase or alcohol, and the reaction occurs, which gives your fructose and your glucose equally. Now this is an acid catalyzed reaction, you have to remember that. So the first method is the hydration of cane sugar, which is the C12H22O11. We are giving H3OH plus, which gives C6H12O6. One is fructose, another one is C6H12O6, which is the glucose. Now you have to remember that both these things are obtained in equal amounts. Alright, so both these things are obtained in equal amounts. Moving on, this is the process of hydration. Okay. Now the sources, from the sources of monosaccharides you can obtain the glucose, now from oligosaccharides and also from polysaccharides. So let's read what is told here. So for a typical polysaccharides containing n units of carbon, you have to say that here, just a minute, n units of carbon, let's write here, containing n units of okay. So for a typical polysaccharides containing n units of carbon, n minus 1 H2 molecules are required for the hydrolysis. Okay. So we can understand this when we study the commercial process of manufacture of your glucose. So what is done here? See, here it is n molecule of your starch or glucose. Okay. So according to this thing, n minus 1 H2 molecules are required, so we are providing n minus 1 H2 molecules and we are getting n units of glucose, right? So this was the commercial method for the preparation of your glucose, and now I come to a new portion, which is the structure of glucose, towards the structure of glucose. Okay. Now this is a portion which deals with that it will prove that the structure of glucose which we studied earlier is true. Okay, now how was the structure of glucose established? Okay, firstly, from the mole concept we got from the mole concept and empirical formula, we found the formula to be of glucose to be C6H12O6. Okay, very good. Now we performed a reaction of your glucose, this is glucose, right, with your hydrogen iodide, which is a strong reducing agent, and we get n-hexane. Okay, now what is the conclusion from this? This proves that all the carbons are connected in straight chains. After that, we treat it with ammonium hydroxide and with hydrogen cyanide respectively. From ammonium hydroxide, we get your oxime, and from HCN, this is your ammonium hydroxide, another one is your HCN. Okay, we get your cyanohydrine. This proves the presence of your carbonyl group. Now you have to remember that this thing we have seen in the aldehyde ketone chapter. So this proves there is a presence of your carbonyl group. Moving on, we have performed mild oxidation with bromine water, right? And we see that gluconic acid is from this aldehyde group is being converted to your carboxylic acid on oxidation. Okay, so aldose is getting converted to aldonic acid. Now when we perform strong oxidation with concentrated HNO3, which is a strong oxidizing agent, then we get glucaric acid. See, in glucaric acid, both the above CHO and this is the aldehyde group are getting converted to C double bond O, COOH, which is the acidic group. Now here, since there was mild oxidation, only one C double bond COOH is produced, and here, since there is strong oxidation, two COOH is being produced. This proves that there is present of primary alcohol. Okay, now if we treat it with the acyl group, which is CH3 C double bond O CH3, then we get a structure of some sort of this. Okay, this okay. So what is the conclusion we get from the above performed experiments? We conclude that glucose is concluded to have 5 alcoholic group and 1 aldehyde group on different carbon, and as the structure is stable, right? So glucose is concluded to have 5 alcoholic group and 1 aldehyde group on different carbon as the structure is stable. Now moving to the stereochemistry of the structure. So the structure was given by stereochemistry structure of glucose was given by scientist Fischer, who gave the following structure, which is CHOH, HOH, OHH, HOH, HOH, CH2OH. Okay. Now if we have in chiral carbon means the carbon which have 4 different types of functional group. Okay, 4 different substituents connected to it. So if we have n number of chiral carbon, then we will have 2 to the power n number of stereoisomer, and only one of them is your D-glucose. And now this is your D-glucose. Okay, D. I'm sorry, I have messed up the writing. So let's write here D-glucose. Okay, so if you have n number of chiral carbon, then we will have 2 to the power n stereoisomer, and only one of them is your D-glucose. Moving on to stereochemistry. Now D represents the configuration, as I mentioned earlier in the above section when I was discussing about the nomenclature of D-glucose. Now D represents the configuration and not related to sign of any optical rotation. I have already said that. DLN indicate the relative configuration of a particular isomer. This is done by using a simple carbohydrates. For example, if we take glyceraldehyde, if OH on the second last carbon, okay, now if OH on the second last carbon is present on the right, okay, then it is called D, and if present on the left, then it is called L. This is, for example, this is the structure of your glyceraldehyde. Just a minute. Let's make it properly. So this is the structure of your D-glyceraldehyde. Okay, if OH on the second last carbon is present on the right, then it is called D. If on the left, then it is called L. Now coming to the cyclic structure of your glucose. Okay, now see, this was the straight chain structure as it was given by who? Fischer, right? Fischer. Now this was the straight chain structure which was given by Fischer. Okay. Now see, here this carbon is getting reacted with the above keto group. Now so we know that the oxygen has a property of plus M effect, so this bond will split this way, right? So here will be a net plus charge, right? So here will be a net plus charge, right? And here will be a net minus charge because it is gaining an electron, right? Don't follow the pain marks for just the time being. You will get to know it. Just follow my annotations in red color. Okay. Now see, oxygen has lone pair here. Okay, and here it finds a positive charge. So what will happen? The oxygen will go and get connected with this oxygen or bond up with this oxygen, right? And similarly, this hydrogen will go from this side and get bonded to this carbon. All right. Now this hydrogen can also follow this way and also follow this way. There are two kinds of direction of attack. Okay. So on the basis of that, the naming of carbohydrates are done. This is the Fischer. Fischer. So moving on, let's drink some water. Just a bit, just a time being. Okay. Moving on. So from that we get some sort of structure like this. See, the H is going from this side, the OH was already there, the H is going from this side, and the oxygen is getting bonded like this. So we get a cyclical structure of like this, right? So you may ask me a question that why the last carbon is only reacting, because if the last carbon is attacking, then there is a possibility of having 6-membered ring, which is considered to be more stable. You have to remember that 5-membered ring and 6-membered ring, it is considered to be more stable than 3, 1, 2, 3, whatever. Okay. So the last carbon is attacking because there is a possibility to make 6-membered ring which is more stable. So, okay, so moving on. See, as I mentioned earlier, this is the anomeric carbon on which the oxygen is attacking. We represent is anomeric carbon. Okay. Now, what is anomeric carbon? Anomeric carbon means this is also anomeric carbon for beta D-glucose. Anomeric carbon is the carbon where the oxygen is attacking and for which there is change in the nomenclature, which is the alpha or the beta, right? A tip to remember which is alpha and one is beta. Which one is beta? See, this OH you have to see, okay? If this OH is found inside this box-like structure, this box means the bonding of oxygen. If this OH is found in this box-like structure, inside this box-like structure, then it is called your alpha. And if this OH, you can see here, this OH is outside this box-like structure, this will be the box, okay? If this OH is outside the box-like structure, then it will be your beta T glucose. This is written over here. Okay. So moving on. So these are the cyclical structure of the beta D glucose and the alpha D glucose. Now, which is alpha and which is beta? I'm telling you that if the H is present above, now the H on the first carbon is present above. This is first carbon. Now the nomenclature. Let's tell how to count the number of carbon. This is carbon number 1. This is your carbon number 2. This is your carbon number 3. Just a minute. This is carbon number 4. This is carbon number 5. This below one. And so gradually this is your number 6. Okay. Counting will always begin from the right side. So if the hydrogen or the OH, so let's get to done with your OH. Okay. So if the OH is present below of the anomeric carbon, AC means not alkyl here. It means anomeric carbon. This AC, right? So if the OH is present below the anomeric carbon, okay, in the first carbon, it is called alpha. Otherwise, it is called beta. Where the OH is present above. Similarly, if you can remember like this, if the H is present means up of the anomeric carbon, then it is called your alpha. Otherwise, it is called beta. Okay. Now there is a question may arise: why there was a need to find out the cyclical structure of the glucose? Why there was a failure of the straight chain? Now when we are human beings, we are always wanting to perform many experiments and to see. We are always eager to find out what happens next. Okay, so scientists perform experiments on the glucose, noting that it was a straight chain structure. They found that it failed to explain the stability of the following properties. Glucose do not show 2,4-dinitrophenol test, Schiff-based test, NaHSO4 test, addition product, and also the pent acetate of glucose do not react with NH2OH to form oxime. Now, what does this mean? See, 2,4-dinitrophenol test. This was a test we have already studied in the aldehyde ketone chapter. Addition product and also this NH4 SO4 and this Schiff-based test. Remember, this Schiff-based test gave red color on the identification of your aldehyde, right? So glucose do not for 2,4-dinitrophenol test and Schiff-based test and NHSO4, and the addition product is this. Okay, the pentacetate of glucose do not react with NH2OH to form your oxime. Okay, if there was straight chain, then on direct reaction it forms oxime, but this does not occur because the oxygen is busy forming the ring. So here is a basic difference between your alpha glucose and your beta glucose. The melting point is this, and melting point of here is this. Crystallization of it is formed by the, so here is the preparation I have mentioned. That's crystallization of concentrated solution of glucose at 303 Kelvin you get alpha glucose, and on crystallization of hot and saturated solution at 371 Kelvin you get your beta glucose. So it is formed by 36% and it is formed by 64%. Now beta D glucose is more stable. You have to remember that. So this is the extra knowledge. If you want, you can learn. This is the 2,4-DNP test of the aldehyde. This is the red yellow color solution. This is not shown by aldehyde ketone as oxygen is busy in ring formation. Aldehyde and ketone. This is shown by aldehyde and ketone, not no. It's not shown by your carbohydrate because the or glucose because the oxygen is busy in ring formation. So we saw the structure now like this just now, and here we have the oxygen. So oxygen is participating in the ring formation, right? So since oxygen is busy, aldehyde is not formed. So this is a ski based test. I have already mentioned that red solution of precipitate is formed when there is aldehyde. Okay, now from here is a very different portion. Now here we will learn about the existence in physical life of the alpha and the beta form of your glucose, right? So what is said here, let's see. There exist in equilibrium alpha and beta forms which coexist in equilibrium and can be interconvertible by straight chain form. So alpha and beta can exist in equilibrium and they are interconvertible. Okay, while the ring formation 5-membered ring is generally more preferred, 5 to 6-membered ring is generally more preferred. I've already mentioned because of stability. Let's write here stability. Just a second. I'm sorry. I'm writing it with the mouse, so it's becoming difficult. Stability. Right. Here is the I. So here it says that while ring formation, the 5 to 6-member ring is generally preferred because of their stability. The configuration of C in CHO is sp2, while in hemiacetal it is CH3. As sp2 carbon is susceptible to attack from both the sides, from above or below, the two structure alpha or beta is formed. Now, when we see that there is when we found that the oxygen is attacking from the last carbon to the first carbon, the first carbon in the CHO is a sp2 carbon, right? So it is suspectable to be attacked from this side also, from left side also, or from the right side also. I have already mentioned that, right? So on the basis of that, there is alpha and beta forms. So if OH on the carbon is inside the box like structure, it is also called alpha, otherwise beta. I have already mentioned this. So carbon 1 becomes chiral, and we have also other 5 carbons. This is not even important. Generally hemiacetal is unstable, but 5 to 6 membered ring are extremely stable. This is the same thing getting repeated. Alpha and beta forms are epimers of carbon at each other at C1. Okay. Now what is your anomer? Anomer is a special type of epimer that differs in configuration specifically at a hemiacetal or hemiketal or hemiacetal form of carbon. That is beta D pyranose, beta D glucose, like that. Okay. Now why this is called pyranose and why this is called glucose? Because in organic chemistry, when this form of structure is present, we call it a pyran ring, and so accordingly glucose is called glucopyranose and ketone is called ketopyranose. See, hence the structure is also called pyranose as the glucose derivative as their glucose derivative they have glucopyranose. Now stability, the alpha is less stable than beta because in beta form the OH is present in the equatorial position while alpha form is present in the axial position. So this you can relate with this trans and cis stability, since trans and cis the same concept is applied here. In beta form the OH is located in the equatorial position while in alpha form it is in the axial position, so this thing is happening. Okay, so moving on, the 5-membered hemiacetal rings are stable due to the ring size. Okay, already mentioned these points. Okay, coming to a very new topic, which is your Muta rotation, which says that the specific rotation of pure alpha D glucose and beta D glucose changes over the time they reach equilibrium, and this phenomena is called your Muta rotation. Now see, I have already mentioned earlier that your alpha D glucose and beta D glucose can coexist rather in equilibrium, right? Now when they attain equilibrium, okay, their specific rotation changes with time. Okay, when they're present in equilibrium, the specific rotation changes with time. Here, when only alpha D glucose is present in a solution, then the specific rotation comes out to be your 112.2 degree, and only when beta D glucose is present or glucopyranose, same thing, at equilibrium. When only beta D glucose is present, it rotates the plane of polarized right into 18.7 degree, and when they both are present in equilibrium, they are present in plus 52.6 degree. Now what happens here is, if you take a test tube here, okay, suppose this is a test tube, and if you have some sort of solution here, okay, now you pass a plane light, okay, now this is your line of incidence light. Now when you keep only glucopyranose, you see that the or the light is getting rotated at this direction, which is 112 degree, and when there is beta D pyranose, the light gets rotated at this angle. So in equilibrium we find that it is coming from the between of these two value. I'm sorry, this is not the line which I meant. It will be from the between of these two lines, like this, like this. This is my test tube, and here I have your solution of beta D glucose and alpha D glucopyranose in equilibrium and in isolated state also. So let's repeat, what is Muta rotation? The specific rotation of alpha D glucose and beta D glucose changes the time over the reach equilibrium, and this phenomena is called Muta rotation. The specific rotation of alpha D glucose is found to be 112 degrees and beta D glucopyranose is found to be 18.7 degrees, and at equilibrium 52.6 degree is found the Muta rotation. Moving on to fructose, which is a ketohexose. Now while I was classifying the carbohydrate, I have already mentioned that if keto group is present, then it is called ketohexose, polyhydroxy ketose, like that, and if aldehyde group is present, then it is called polyhydroxy aldose. Then fructose under that category is your ketohexose. Hexose, why? Because there is 6, and ketone means because there is C double bond to this group. Okay, now let's see the straight chain structure of your fructose. All right, so let's see how many carbons are there. This is 1, this is 2, this is 3, 4, 5, and here is 6. Now see the second last carbon, there is oxygen. Similarly, the oxygen is attacking here. So let the bond first open up. The bond is first opening up. Don't see the blue arrow marks for the time being. So minus is coming here, right, and plus charge is coming here, right. Now all this oxygen has lone pair of electron, right. Now why this oxygen is only attacking? Because and this are not attacking, because from here if they attack, there is a possibility to form 5-membered ring which is more stable. Okay, so there is electron present, lone pair of electron present with this oxygen, right? And we know electrons are negatively charged, so it will find and attack this carbon which is already having the positive charge, because it lost an electron which is taken by your oxygen. So this lone pair goes and attack here, and similarly this H will go and attack from behind to the oxygen which has gained one electron. See, so some sort of structure like this is being formed. Let's join this. So a structure of some sort of like this has been formed. This is the oxygen. This oxygen. This oxygen is this oxygen. Okay. So a structure of some sort of this is formed. This is the beta D fructose. Right. So moving on. The fructose are also called levers because it is levorotatory, because it can rotate the plane of polarized light in a direction which is opposite to your dextrorotatory. So it is called levorotatory. So this is the structure of your ketohexose. It is called D minus minus fructose. So this is the furan ring. It is also called furan ring. For glucose, there was a 6-membered ring. It is called the pyran ring, and this is called the furan ring. Okay, this thing. So this is the structure of your fructose. Okay. So anomers of fructose are, unlike glucose and fructose is practically seen in 6-membered ring, are formed very small quantities, and relative formation of a 5-membered ring is more frequent. Unlike glucose, in fructose, it is seen that 6-membered ring are formed in very small quantities, and relative formation of 5-membered ring is more frequent. Now you may ask me a question, why there is only this pentagonal structure, why not a hexagonal structure? Because hexagonal structures are also formed, but the 5-membered ring structure is more stable, so it is more frequent. So this is the structure of beta D glucose and beta D fructose. Similarly here you can remember it this way. Let's remember it with oxygen, with OH minus. If the in the first carbon, which is 1, this is 2, this is 3, this is your 4, and here is your 5, and here is your 6. Okay, so I'm sorry, this carbon will be 1. Okay, just a minute, I am correcting it. Sorry. So this will be carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, this is your 5, and here is 6. Okay, so here you can also remember it this way. If the OH on the second carbon is present below the anomeric carbon, then it is called alpha D glucose, and if it is present above, and if it is present above, then it is called beta D fructose. Now if we come to the reaction of glucose and fructose, it generally shows similar reaction. Okay, moving on. So glucose and fructose generally show similar reaction. Alpha hydroxycarbonyl is known to show positive results for Benedict and Tollens test, and glucose fructose show positive results for Fehling test and Tollens test. Okay, so the Tollens test is also called the silver mirror test. You must have done in the practical exams. A silver like coating is formed around the test tube, right? This is the Tollens test and the Fehling test. In Fehling test, you take the two kinds of solution, Fehling A and Fehling B, and in the Benedict test, you take the copper citrate solution and you get the carboxylate ion and the CuO, which is the brick red, which proves the presence of your fructose. Okay. So next comes the reaction of glucose. So glucose can be performed reduction with the help of sodium and the ethyl alcohol. Okay, which is the mild reducing agent. So this is getting converted to your alcohol, right? Because we know aldehyde can be reduced to your alcohol with the help of mild reducing agent. Okay. Now if we take strong reducing agent, both the CHO group are getting converted to your N-hexane. See a straight chain like here is found N-hexane because helium iodide is the strong reducing agent. Moving on, reaction with CN. This aldehyde group is converted to CN. You can see here. Okay. This is glucose and this is CH2H. We get cyanohydride and on one or more carbon, C atom becomes chiral. Right? This C atom is becoming chiral C. This C atom is becoming your chiral. So next comes disaccharide. Now to form disaccharide, we need to join two kinds of monosaccharides. Okay, so monosaccharides plus monosaccharides give you disaccharides. So examples of disaccharides are sucrose, maltose, and lactose. Okay, so before coming to sucrose, before coming to the portion of sucrose, we just revise from the second portion. So let's go to that portion. Okay, so we are back. We are going to revise what I have told you up to the disaccharides. Okay. So from the preparation of glucose, so glucose can be prepared by the hydration of your cane sugar, which is C12H22O11. If you perform the hydration by the acid catalyzed reaction, we get a mixture of your fructose and glucose in equal amounts. So in what way the hydration is performed? We take the sucrose, we boil it in the presence of the enzyme invertase or in the presence of your alcohol, and the reaction occurs and we get fructose and glucose in equal amounts. Now this was about the sources. I'm not getting into the complexity of this. Now here is a note. So for a typical polysaccharide containing n number of units of carbon, n-1 H2O molecules are required for hydrolysis. Now this is the commercial method from starch, which is the C6H10O5. If you take n units of starch, which is C6H10O5, and you then need n-1 molecules of H2O to produce n units of your glucose. Now evidences of the structure of glucose. Why glucose has a structure of that straight chain? We found the molecular formula of glucose is like C6H12O6, and this was the empirical formula from the mole concept. We find out this. After that, we performed your strong reduction with the help of your hydrogen iodide. Okay, and we got N-hexane. This proves that there is a presence of carbons which are connected in straight chains. So after that, we performed reactions such as ammonium hydroxide and hydrogen cyanide. So we got oximes and cyanohydrin. So these are the reaction of your aldehydes and ketones. So which this proves there is the presence of your carbonyl group. After that, we performed mild oxidation with the help of bromine water. So this carbon was oxidized and we got carboxylic acid. The acidic structure over here. And since it was mild oxidation, so only one CHO group is being replaced by COOH. So if we perform now strong oxidation with the help of concentrated nitric acid, with this both the COOH groups becomes reduced. Oxidized. Okay. So this was about the alkylic substitution with the help of pyridine. So conclusion from this is that glucose is constituted to have 5 alcoholic groups and 1 aldehyde group and on different carbon, and as their very structure is very stable. Now stereochemistry, from the examination of stereochemistry, glucose, the feature gave the structure of your T-glucose. Now if you have n chiral carbon, we will have 2 to the power n number of stereoisomer and only one of them is T-glucose. Now from the stereochemistry, D represents the configuration and not related to any sign of optical rotation. D and L indicate relative configuration of a particular isomer. This was done using simplest carbohydrate glyceraldehyde as for reference. If OH on the second last carbon is present on the right, then it is D. If left, then it is called L. Right? Next, I'll come to the cyclical structure of your glucose. So I already said how this structure is already being formed. Okay. Only the last carbon attack because there is a possibility of making a 6-membered ring which is more stable. So here these structures are being formed if OH is present inside the ring, which is called alpha. If outside, then it is called beta. This is called the anomers. The anomeric carbon is the carbon for which the entire configuration or the alpha beta configuration is being changed. Okay, so why did the straight chain now fail? The straight chain structure failed to explain the stability because of the following properties. Now the first one, which is the glucose does not show the 2,4-dinitrophenol test, which is shown by the aldehydes which have straight chain. It do not show the Schiff base test and also the sodium hydrogen sulfide test and also the addition product test. And the pent acetate of glucose does not react with NH4OH to form oximes. Okay, so those straight chain on the direct reaction forms oxime cyclic structure doesn't. So I have already mentioned that. So here are some properties of alpha and beta glucose. These are the melting points and here are the preparation methods. Okay, so 2,4-dinitrophenol test, this was a Schiff base test. Okay, they exist in equilibrium. They coexist in equilibrium, the alpha and beta form, and they can be interconvertible. Okay, while ring formation, 5 to 6 membered ring are generally preferred because they are more stable. I have already mentioned the configuration of C in CH2 is sp2, so it is susceptible to attack from both the sides, which lead to the formation of alpha and beta structures. Generally, the hemiacetal is unstable, but 5 to 6 membered ring are more stable. Okay, anomers are a special type of epimer and that differ in configuration specifically at hemiacetal or acetal carbon atom. In the ring, the numbering starts from the right. I have already mentioned that. See, this is the pyridine structure. Since the structure is called pyranose as glucose derivatives, they are called glucopyranose. So the stability of beta glucose is more than the alpha glucose. I have told you to remember the concept of trans isomerism. In beta, the OH is in the equatorial position, while in alpha form, it is in the axial position. Okay. I'm sorry. The 5-membered hemiacetal ring are stable due to the ring size. Okay, so what is Muta rotation? The specific rotation of alpha and beta glucose changes over the time they attain reach equilibrium, and this phenomena is called Muta rotation. This is the angles and this is the equilibrium angle. So coming to fructose, so fructose is a straight chain structure. This one is shown here, and I already shown how this ring-like structure is formed. So fructose is called levose because it is levorotatory. Moving on, anomers of fructose, unlike glucose, in fructose practically, it is seen that 6-membered ring is also formed, but in small quantities, so 5-membered ring is more frequent. This is an experimental thing. Okay, so moving on, glucose and fructose generally show similar sort of reaction. Okay, the alpha hydroxy carbonyl is known to show positive Benedict test and Fehling test and also Tollin test. So the glucose and fructose show positive results for Benedict, Fehling and Tollin test. So this is the reaction. This is the Elliott-Ketone chapter reaction. Okay, so this is the Benedict solution, which is a copper citrate solution, and we obtain the carboxylate ion and the brick red color of copper oxide. Okay, now we perform the reactions of glucose under the reaction of glucose. This is the reduction, which is the mild reducing agent. We take sodium amalgam in presence of ethyl alcohol. So this CHO is reduced to alcohol is CH2OH. After that, we perform strong oxidation. So both the A is being reduced, both the CHO groups is being reduced, and we get a straight chain structure which is N-hexane. And after that, there is reaction with HCl, which is CN, which is the aldehyde. In the chapter we have aldehyde and ketone, we have already studied it. So CHO gets converted to CN. We get cyanohydrogen and one or more C atoms becomes chiral. So this carbon atom is becoming chiral, right? So this is the disaccharide portion. To form disaccharide, we need to combine two monosaccharides. This is obvious. So monosaccharide by monosaccharide, we get disaccharides. Example of disaccharides are sucrose, maltose, and lactose. Now from sucrose, we will do in the next lecture because it is becoming very long. So I'm coming in just a second to start the new lecture. Till then, keep studying. All the very best.